8-2 is similar to 8-1, so hopefully we can reinforce some things and make some things a little easier. We have a satellite traveling around Earth in a circular orbit at a constant speed and a constant distance. An identical satellite is set into orbit around a new planet. The new planet's radius is the same as Earth, but it's significantly more massive. The satellite orbits the new planet with the same orbital period. Is the distance of the satellite from the Earth greater than or equal to D? Okay, so I've put out here again the gravitational force being equal to a centripetal force. That bears repeating, okay? And what I didn't write here, but I'm going to write now. Since the periods are the same, right, and the radiuses are the same, and since v is equal to 2 pi r over t, then the velocity is the same. Okay, Okay, so I solved this for r, and I got this. So what's our r new? Okay, again, we're going to do our sort of qualitative factor of change method. Big G stays the same. The mass is increasing, and the velocity is staying the same. So the new radius is larger than the old radius. Okay, 2 points there. One for saying the new orbit is larger, and also, which they weren't really clear on this, but this is what the rubric said. What needs to happen then, if the period is going to be the same around a larger orbit, then the velocity needs to increase. Now, I don't know how you were supposed to come up with that. I mean, it's not difficult, but they didn't really ask you to think in that direction. So you may have only gotten one of those 2 points, but this rubric says 1 point for saying that the satellite must increase its speed to maintain its period. Okay, so part B, here we are again on the internet looking up formulas, which is always a good idea. Well, it's a good idea if you know that you've got good sources, right? So hopefully you've learned what some good sources are. So they tell us that RV squared over M is equal to C, and they ask us if that's consistent with part A. So this explanation is maybe a little more complicated, but here it goes. So we're trying to confirm that if the mass of the planet increases, then the radius of its orbit must also increase. So what we know here is that the mass increases. So if the denominator of this fraction increases, then the numerator must also increase. Okay, now they've told us that period is going to stay the same, but remember that v is equal to 2 pi r over t. So then this numerator now becomes r times 4 pi squared r squared over t squared, because I just squared v there. So this must increase. If the period is going to stay the same, then the radius has to increase in order for this c to remain constant. So we had to kind of dig down a couple of layers into this, but it is consistent. So we get 1 point for saying yes and attempting to establish a functional dependence. 1 point for arguing that if t increases, then r must increase. If t stays constant, r must increase. And then 1 point for realizing that the mass of the planet is going to increase the distance. So that one was a little bit funky, but 3 points for part B. And now, just like in part A, the rocket's going to do a burn and end up in this smaller orbit. Well, in order to do that, we need to slow the planet down, because we know that stuff that is orbiting closer to the planet is going to be going with a smaller orbit is going to be going slower. So what had to happen at point A then is the rocket had to fire in the opposite direction of motion. So 1 point for saying that it's firing opposite, and 1 point for explaining that in order to decrease its speed, it needed to create a force opposite the direction of motion. So that's part C. All right, so D, E, F, and G are students 1 and 2 again. Now we're in this smaller elliptical orbit for a while. And student 1 says the satellite's moving faster at point A because the total mechanical energy of the satellite Earth system is constant. And we were on the right track there, but remember the satellite's going to move fastest when it's closest to the planet, so it's actually moving slowest at part A. But the mechanical energy is constant. So number 2, the second statement, is correct. Number 1 is not correct. On to student 2, the satellite's moving faster at point A because gravitational potential of the Earth energy system, of the satellite Earth system is higher at point B. Okay, once again, one of them's right and one of them's wrong. He's right in saying that the satellite's moving faster at point B. However, it's moving faster because the kinetic energy is higher. The gravitational potential energy of the satellite Earth system is actually at a minimum there. So there's the 4 statements, 1 point each. I promise there's one coming up where both of the statements are wrong or both of them are right. It's not always one right, one wrong. So don't get sucked into that. If you think they're both right or wrong, say so. Okay, part H, we're back to these graphs. Okay, and you got to read carefully, as you probably learned in the last question. Which of the following of the above graphs best represents the potential energy of the Earth satellite system as it orbits? So we know that there's more gravitational potential energy at A than there is at B. So we're going to look at either graph 1 or graph 2. So you can see in graph 2, there's actually more at B and less at A. Graph 3 might suck you in, but at A, the numbers are smaller negative numbers, so they're actually bigger numbers. So you got to do a little bit of algebra, witchcraft in your head there, but -3. Also, remembering that gravitational potential energy is always negative might have sent you to the correct graph right off the bat, which is fine. Just make sure you go through and make sure that the other ones are incorrect. So 1 point for graph 3, 1 point for relating the gravitational potential energy to the distance from the planet. Finally, part I. Which of the following graphs represents the torque about the center of Earth exerted on the satellite by Earth? So if you think about the gravitational force, right? Here's Earth, here's my satellite. The force is this direction. The object is moving this direction, okay? So that's a 90-degree angle, so there's no net torque on, let me read this correctly, on the satellite by Earth, okay? It's moving this way, but the lever arm, right? The force is this way, the lever arm is this way. Sorry, I shouldn't have drawn this vector here, okay? So the theta here is, it's not 90, it's not 0, it's 180, okay? So the torque is equal to 0. So we want graph number 2, okay? So we've talked about this before. There's no net torque. There's no net work done. That's why mechanical energy remains constant. So for part I, 1 point for saying graph 2 and 1 point for the correct explanation.